or corporate email IDs. So if you are working here, or if you are a student, you have a student email ID of your university or college, use that email ID so that you will get more amount of licenses. And if you are using a corporate email ID, that also will be helpful to get more amount of licenses and different flavors of EDA tools. Okay, for simulations. So we have different EDA tools for simulations from Cadence and Synopsys and Mentor Graphics. So the most famous ones from the Cadence are NCSim, that is Iron or Exilium, Extra. And from Synopsys, this is very famous tool, VCS, Very Low Compiled Simulator. And the most open source and user-friendly tool from Mentor Graphics Siemens is Model Sim or Cluster Sim. And the other most useful for FPGA is Xilinx, ISC or Xilinx Vivado. This is from AMD. Okay, so AMD and Xilinx are merged together. Okay, so Xilinx AMD we call. So we will get Xilinx ISC and Xilinx Vivado. So this is for FPGA. So using these tools, we can install in our laptop Xilinx Model Sim Cluster Sim. But to work on Exilium or Iron or VCS, we need to have a EDA Playground account. That is also for academic emails or corporate emails. So if we are using our personal emails, we'll get only iCaras Verilog or MC Verilog. These are open source tools. So after creating the registration or login, you will be having two windows. So one window is for test bench and other window is for design. Okay. So in the test bench window, you have to write a test bench Verilog code. In the design window, you have to write a design Verilog code. Next, select the simulator you want to choose. And to plot the uniform graph, you need to do the additional settings that you have to select the simulator. For that relevant simulator, you have to put a waveform generator. Then click on run. Then it will generate a waveform timing diagram. Then you can observe the results and try to debug the code if you have any errors or functional errors. Clear? So next is, as a course of our project, we have learned, okay, a simple project about carry select adder, and we have compiled the Verilog code using this carry select adder. So in carry select adder, we have three stages. One is triple carry adder, and the other one is binary to excess-1 converter, and the other one is multiplexer. So in the traditional one, we have two sets of triple carry adders. So in the initial architecture level, we have modified the second stage of triple carry adders to BEC, that is binary to excess-1 converter. So these are very important digital circuits in our life, which plays major important role when we are going for an interview. So as a part of your course subject, digital electronics or digital design through Verilog, what project we have done? So this is the important question our interviewer or any outside person will ask you. So at that instance of time, you need to be in a challenging position to justify the answer to the interviewer. So as I am a student, so I have done a learning project, okay, based on Verilog and digital electronics. So using this, I have started learning, okay, adders, triple carry adders, and carry select adder. So from the traditional triple carry adder, from the traditional carry select adder, I have modified and learned the observation of optimizing the design at architecture level by reducing the hardware. So hardware is nothing but gates. So example, consider one triple carry adder takes, okay, 4 bit. So that is 4 half adders. So to add 1 bit, we need another half adder. Instead of that, what we will do? We will use binary to excess-1 converter. So that is, we are adding only 1 half adder instead of using 4 half adders. So that is how we have optimized the design in the second stage to avoid using triple carry adders. So this is directly a modified carry select adder. At last, based on your carry, okay, select carry input. So your sum will be generated based on the multiplexer you choose. So this is a simple Verilog code top level. So here we have used a concept called module instantiation of full adders. Okay, triple carry adders. So full adder is instantiated here, and triple carry adder is instantiated here. Okay, and binary to XS1 converter is instantiated here, but the codes of individual are written here. So this is the test bench. So test bench we are passing test vectors for A bit, B bit, and Cin. If Cin is 0, it will go for directly DEC XS1. So this is how the IDA playground looks like. So this is your test bench column, and this is your design Verilog code column. So based on this, you have to choose your Verilog simulator and what type of coding you are writing, you have to choose. So you are trying to choose system Verilog or Verilog code. Next is you are choosing tools simulations. So we have different types of tools, like I have told you. So IIDT, Cadence, Exilium, Synopsys, VCS, Siemens, Vestasim. Okay. So if you don't have your student email account, you will be seeing free simulators. Okay. GHDL, ICARS Verilog. These kind of simulators you will be seeing. So if you have a registered email of your university, college, or corporate email ID, you are using this email ID for registering in the EDA playground, you will get commercial simulators. Clear? So this is what I have to stress on the. Next, after running the simulation, you will get a timing waveform diagram like this. Okay, so you might be experienced with this. Next concept is finite state machines and digital circuits. So finite state machines are like algorithm or flow chart, what we see in our C programming language in our engineering first. So the similar way to generate hardware or to write a behavioral Verilog code or a behavioral hardware description language, they use finite state machines. So there are two types of finite state machines, Mealy state machine and Moore state machine. So Mealy state machine, a finite state machine is said to be a Mealy machine if output depends on both present inputs and present states. So we have a system, that system will depend upon its present inputs and present states. Then it is called a Mealy state machine. Next is Moore state machines. A finite state machine is said to be a Moore state machine if the output depends only on the present state. Okay, present state. So there is no external input to the system. So it will depend only on the present state. So currently the lift is in 4th floor. Okay. So what is the state machine replicates? It is in the 4th floor only. But whereas if we give external input, okay, so then it will become a input state. So the machines which depends only on the present state are called Moore machines. So based on the state machines, okay, basically in real time we will be using Mealy state machines where we depends on input state and the present state. So Moore state machines we use less in our real time applications, very less. So based on the state machines and inputs we pass, and we'll represent a excitation table or truth table. So next is ASIC design flow and synthesis. So as we have learned ASIC, application specific integrated circuit. So design flow, next is design flow explanation, tools used during each step, synthesis for flow, inputs for synthesis, timing constraints, outputs of synthesis, netlist example. So integrated circuit, what is an integrated circuit? Semiconductor chips are small semiconductor wafers that hold millions of tiny electronic components. So what is an integrated circuit? This is a textbook definition. Okay. So an electronic IC circuit, okay, which consists of millions of electronic components, which are connected together on a silicon wafer, tiny silicon wafer. So then it is called as a uh, semiconductor chip. So all the circuits in a single die substrate. So whatever the electronic components that we interconnect together to build a circuit will sit on a single substrate. IC fabrication. In simple terms, a semiconductor foundry is also known as a fab. Okay, is a factory where silicon wafers are manufactured. So silicon wafers are manufactured basically from sand. So they'll collect very pure form of the sand and they'll filter it, okay, selective sand, and they will overheat at a high grade of temperature to form a wafer. And based on the dopants, either they form a p-type semiconductor or n-type semiconductor. And in such a way, they'll prepare a wafer. So learning all these concepts beneath, okay, the wafer level is applied physics or device electronics. So we have many tools to learn device electronics. So if you want to design a transistor, okay, so how will you design a transistor? You have a wafer. Based on the wafer, okay, you want to design a NMOS transistor. So we have to create a source, drain, gate, three terminals. So when we supply a voltage, okay, gate voltage, the flow of charge from source to drain has to charge based on the channel length. So what should be the dopant concentration? And what should be the channel length? All these parameters are related to device modeling. So these device modeling tools are example, Silvaco. Okay, you can check in internet. Silvaco, TCAD, that is from Synopsys. Okay, so most of the tools for device modeling where fab companies like TSMC, UMC, Global Foundries, or XFAB, XMA, Samsung, Intel, they use a wide variety of, okay, device modeling tools to create cell libraries. That is how IC semiconductor foundry works. Next is IC design. So IC design is on the top of fab, IC fab. So IC design companies are like Intel, Qualcomm, AMD, and NXP, Philips. Okay, all these companies are MNCs for IC design. And EDA tools like Siemens, Mentor Graphics, Cadence, Silvaco, Synopsys, all these are EDA tool application companies. So we have jobs in all these domains if we are learning VLSI subject. So in VLSI subject, we can go for a specialization of VLSI front-end design. In front-end design, only Verilog coding or design modeling. Okay. And next is verification. And next is synthesis or physical design. Synthesis, physical design. And next is DFT engineer. And next is physical verification engineer. And next is layout engineer. And next is analog circuit design engineer. Analog circuit design engineer. So all these are the different variety positions in VLSI. And at last, we have non-technical positions also in VLSI. Okay. For PCB, board design, integration of ICs on the board level. These all are also electronics hardware related jobs. So in IC design, EDA tools helps in designing, optimizing area, power, and timing, and verify electronic cycle. So what we have done, we have written a Verilog code using verification. Okay, writing a test bench, we have checked the design functionality. Okay, and using synthesis, we have verified the netlist, area, power, and timing, report area, report power, report, and timing. So there are very much advanced in the tools of Cadence what we are learning. So they have indulged artificial intelligence and machine learning in the tools also. So in couple of days back, that means that is on Wednesday, I think, I have attended a Cadence forum technical talk in Hyderabad in a Westin hotel. So they have introduced artificial intelligence and machine learning in the tools also. So we have to update our tools. Okay. So based on the licenses what are available for us. So when we are doing the floor plan placement, routing, clock tree synthesis, and ECOs. Okay. So we are doing it in the form of repeatedly. Right. Repeatedly. So what is our major constraint is we have to meet the goal of area, power, and timing in our chip. We have to very small in size. The chip size has to be very small. Okay. And it has to reach the targeted goals like power consumption. And if you have congestion, what is our problem? And what is a IR drop? If we have very much IR drop, what we should do? And there is burst negative slack, and the total skew is damaged. Okay, related to timing. So what we have to do all this? So initially, when we are setting up the design, okay, for physical design, floor plan, placement, route, CTS, and routing, the tool will learn what are the steps we are doing. So machine learning is nothing but teaching the tool what it has to do. Okay. So same way, the tool is learning whatever the steps we are doing. And later on, the tool will generate different case scenarios. How to fix your area, how to fix your power, how to fix your timing. So anyhow, in VLSI, we have a trade-off between area, timing, and power. Trade-off means if we are going for area compromise, okay, we can fix power and timing values. If we are having a area constraint, okay, we will have a trouble in area, timing, and power. So there is always a trade-off between these three components. Somehow we have to sacrifice. But meeting all together is a big challenge. So this is how the tools are getting trained by itself based on our inputs or the steps how we are doing. And later on, okay, by changing our iterations, as we have seen, clock tree synthesis was taking around 10 iterations and routing was taking around 15 iterations, like incremental placements, incremental routing, global routing, nano routing. All these concepts have been done in the incremental steps, iterations. So while doing all these processes, there are some algorithms going in the background of EDA tools. So how are these algorithms developed? Based on some mathematical calculations. So the math and computer science sitting together, they have developed algorithms to design circuit to play EDA tools. So we are the designers of circuit or electronics boards, okay, and the computer science people using maths and computers software programming, they are developing these EDA tools, and using machine learning algorithms, we are creating a different scenarios to generate better results. So this is how the tools has becoming more advanced to help humans Okay, so there is another update in the industry also. So there is a chip called Blackwell. This is from NVIDIA. This Blackwell chip is developed in 2 nanometer technology. Okay, so sorry. So the Blackwell chip is designed in TSMC 4 nanometer technology. Okay, this is the world's biggest amount of transistors sitting on a chip, 208 billion transistors, and it is custom design. You know what is the difference between custom design and normal design? So in normal design, what we do, we will automate the tools to form a circuit. Custom design is nothing but analog circuit design. So using TSMC 4 nanometer process, Blackwell chip has been released. So this is one kind of processor. Okay. So this is very famous GPU from NVIDIA. So this chip has 208 billion transistors. So you can understand the specifications of this chip. So as the technology is shrinking, the tools upgrades are also becoming more intelligent. And the engineers are saying they have to use their skills to design the circuit and use the tools in an efficient way. Hope you are clear, everyone. So far, you are with me, understanding? Dear students, participants. Yes, sir. Ram Babu. Yeah, yes. So based on the scaling, we have different amount of scales in integration. SSI, MSI, LSI, VLSI, ULSI. So in SSI, we have number of transistors or number of gates per chip are 1 to 10 number of transistors. In MSI, we have 110 to 500 amount of transistors. In LSI, we will have 500 to 20,000 transistors in a circuit. And VLSI will have 20,000 to 10 lakhs transistors in a circuit. And ULSI will have more than 10 lakhs. Okay. So this is the integration scale. So next is ASIC design. So ASIC design flow is nothing but application specific integrated circuit. So we are designing a specific chip, okay, only for one particular application. Specifications, okay. So those are on the top level. So here, some customer has given me some specifications to design a Bluetooth chip or graphical processor Bluetooth chip. Next is on the top level, manager or architectural level engineers, they will design a block diagram on the architecture. Next, diving into the architecture, sub-blocks or blocks, okay, RTL designers will try to understand the algorithm or the blocks internally in the architecture and start writing the RTL code using Verilog PhD. Once the RTL is designed, okay, this RTL is passed to verification. Verification team will take this RTLs from the front-end design engineers and will perform physical, logical verification. Sorry. So that is RTL verification. They will be using different methodologies like UVM, VMM, and OEM. So these all are RTL verification methodologies. So if you have a scope of learning verification, we can get a job set RTL verification. Next is once the RTL verification is passed, then the RTL team will give the Verilog code, final Verilog code to synthesis team. So synthesis team, they will understand the code. Okay. They will ask for the design constraints. Okay. If they don't have design constraints, they'll sit with the manager and write the design constraints. They load all the libraries related to technology library, timing library, area library, power library, labs, and all these libraries are loaded to the synthesis. So the process of synthesis is converting your RTL to gate level netlist. So once the synthesis is done, okay, that is the floor plan. Before going to floor plan, we are going to insert scan cells in the synthesis, okay, using netlist. So that is how we are learning the concept of DFT. Next is floor plan. Floor plan is nothing but deciding the chip die area and core area. So once the chip die area and core area is decided, okay, we want to place the standard cells and macros in our design. Placement is completed. Once the placement is completed, we are trying to analyze condition, area, time, power, and the placement. Once the placement is completed and analysis reports are better, then we'll proceed it for CTS, clock tree synthesis. So after clock tree synthesis, okay, we will go for timing analysis, setup time analysis, fail time analysis, power analysis, area analysis, congestion analysis. Once the three components are clear, then are better, then we'll proceed it for routing. So in the routing stage, we will route the signal nets. So after routing the signal nets, okay, the complete layout is ready. So what we will do? We will do sign off checks. Sign off checks like DRC, LVS, DFM, and I am back annotating the Verilog netlist after sign off to the LEC tool to check the design function. Whether after layout, my design is working similar like RTL design or not. If it is working, we will go for fabrication. Once the fabrication is completed, we will get it done for packaging and testing of the chip. The testing. Hope the ASIC design is clear. The first question, the people who are appearing in interview for physical design is ASIC design. How best the ASIC design flow you illustrate to the interviewer, that depth your subject will be analyzed. Okay, initially you have to give the top level overview of ASIC design flow. Then next, you have to detailedly explain in each step how the user inputs or the designer inputs are given to the tool and what tool does and what outputs comes and how analysis are done. These four things need to be taken care as a physical design or any logical design. So once the ASIC design flow is completed, so I am taking an example of specifications of system on chip. In system on chip, I have a different blocks. Regular blocks are more performance blocks, and blue color blocks are RF blocks that are communication blocks, and greenish yellow color blocks are mixed signal blocks. Memory, MEMS, and light sensing. Green color blocks are digital elements. So ASIC design flow, we will write a RTL code. So RTL code is sent for verification. Writing a test means we will verify the design. And after the design is verified, RTL verification is passed, we will go for synthesis. Synthesis is a process of converting your RTL code to gate level netlist. Okay. So once you map the technology library and optimization is done, you will get a RTL Verilog code netlist. So we see the, sorry to interrupt. We see the difference between Verilog code and synthesized netlist, that it is mapped to the technology library primitives like NAND gate inverter or and inverter, XNOR, flip-flops. So we have written an English Verilog code. For this English Verilog code, we have generated a hardware description language netlist, Verilog netlist. So this is synthesis. So once the synthesis is passed, okay, whether my synthesis netlist is correct or not, how we should justify. So to do justification, what we will do, we will take the Verilog model files provided by the technology library, okay, and our Verilog netlist and our test bench. We will give these three inputs to our logical equivalence check or LEC tool. That is formal verification. Once the formal verification is passed, then we'll proceed for physical design. In each and every step of physical design, we'll do this kind of activity, formal verification. Functional verification equal to formal verification, then only each and every step of physical design is successful by a design engineer. Else, we need to fix the violations or any errors caused in the physical design. Clear so far, everyone? You are able to catch me? This is very important. Dear students, you are with me? Someone please reply. Yes, Ram Babu. Next is, yes, sir. Thank you. ASIC design flow. So in ASIC design flow, after synthesis, we are going to insert DFT scan cells. So these scan cells are used just to check the logical, okay, functionality of cells on an emergency basis. So it's like this practical example. So you all classmates are going for an excursion. All the 50 students or 40 students of your class are going for an excursion. So you all have your mobile phones. So what your parents does is, initially they'll try to reach your phone. Okay. When they get failed to reach your phone, they'll try to reach your nearby friend phone. Okay. If the friend phone is not connected, then they'll directly reach another friend. Like that, similarly, they'll try to reach your external guardian who has guided your tourism. Okay. The same way, we have all the options to reach the functionality of these cells in DFT. But while manufacturing the chip, we may lose the connectivity, or there may be some violations due to which the logic gets failed. To avoid this mismatch in the design failures, we use scan pins. So whether the cell is working correctly or not, using these scan pins or scan cells, we will directly check the logical behavior of the circuit. This is how DFT helps. Designed for testability. So after DFT, what we will be doing, we'll go for the floor plan. In the floor plan stage, we will decide the area and area of the chip, core size and die size. Aspect ratio is the concept of deciding the height and width of the area of the floor plan of the chip. Next is core utilization. So how the core utilization is calculated? Standard cell area plus macro area divided by total core area. So the core utilization should be 60% or less. Okay. If you are giving the core utilization at the floor plan stage 90%, then there is only 10% resource for clock synthesis and routing or E0s if you have any violations. So better, how good the floor planning is, then the placement, CTS, routing will go that better. Okay. In the initial step, we have to take care about floor plan. The floor plan should be very strong. That is, we have to decide the core utilization should be 60%, 40%, or 30%, or 50%. Based on the standard cells you have, macros you have. And how much routing resources you need to communicate between macros, standard cells, and all these things. And if you are creating blockages, or if you are creating halos, or if you are creating any boundaries for the macros or standard cells, then you need more area. If you have more pin density and you have more pin density routing nets, okay, between two macros, then your standard cells should not be placed in between these two macros. Then you need to put a soft blockage or a hard blockage based on your convenience. If you are putting a soft blockage, okay, the standard cells which are communicating with the macros which are near to each other, they will sit in the soft blockage. We can manually move them in the top, right, left, or either side of the manual. So this is how we are deciding at the floor plan stage. Next is placement. So in the placement, we are doing a step called placing of our standard cells. So standard cells are of equal height, but they vary in their width. So we will place all the standard cells in these tile regions. So tile regions means in these fallow lines. In between those fallow lines only. That is height and they have a standard height. So our ability is there to place the standard cells in that fallow lines. So we will go with global placement, incremental placement, and detailed placement. 3 stages. So global placement, it will try to check all the possible best places to place the standard cells. Once after placing them, okay, it will estimate the congestion. If there is congestion, it will go for placing incremental. Once after the incremental placement, still we have congestion, it will go for detailed placement. So after placing the detailed placement, we have a command in tool, legalize the placement. So legalize the placement means if we have a congestion of 1%, it will become into 0.12%. That much legalization action will be taken on the standard cells. The detailed legalized placement. The next step is clock tree synthesis. So in clock tree synthesis, we will define the source clock pin, okay, which is taken from the synthesis. Okay, the clock source pin is decided in the synthesis step in STC. So that clock source pin will be called here in CTS, and we'll locate it and try to create a clock tree synthesis so that each and every flop in the design will get reached to the clock in equal amount of time. So that is the main goal of clock tree synthesis. So whatever the distance might be, whatever the drive strength of the flop might be, whatever the drive strength of the net might be, okay, the clock tree synthesis main aim is to send the clock to all the flip-flops at different destinations in equal amount of time. That is balanced clock tree synthesis. Practically, this will never happen with the tool. If you have 10 or 15 number of flip-flops, then this can be done. But we never have 10 or 15 number of flip-flops. Even we have 100 numbers of flip-flops or 500 number of flip-flops, also we can get 0 skew. But never the designs for the physical design are of 1000 cells, 1000 flip-flops. They are in 10 lakhs or more than 1 crore or 10 crores. So it is never possible to practically to reach all the flops from the source clock pin to all the flip-flop destinations elements. And we will have multiple clocks also. One clock is 10 megahertz, another clock is 20 megahertz. Okay. So in clocks also we'll have different clock pins, clock source pins. So so as we have seen in SOC, we have a diagram. All the clock pins of different blocks operate at different frequencies. And at last, we will be building one SOC. How is it possible? So each and every block has different clock source pin. And the main source clock pin is connected to the crystal oscillator on the board. In the process of balancing the clock skew and minimizing insertion delays in order to meet the timing and power. So this is the step of clock tree synthesis. Next is routing. So this is how the routing or the 3D image of layout looks like in physical design. So we have seen this, right? 3D view. So in routing stage, it will route only the global nets that are signal nets, like input to output, input to flip-flops, input to macros, macros to macros, standard cells to macros, macros to output, standard cells to output. These kind of signal connections are done based on the lower metal layers, like metal 1, metal 2, metal 3, metal 4. And the top metal layers like metal 8 and metal 9 are used for power routing. And metal 7 and metal 6 and metal 5 are used for clock tracing. And lower metal layers are used for routing. Okay. So routing is divided into two parts, global routing and detailed routing. Global routing will give you the estimation of routing congestion, area, power, time. And detailed routing will give you the incremental routing of nets between all the elements of our chip and give you the better results. If there is assumption, we have a better results. So taking those design forward, we need to fix the violations of area, power, and time. Okay. Once it is sometimes the tool also while routing, it will try to possibly find the routing paths. Sometimes I have seen cases, it leaves blank. That means it is unable to route the dead end of the net. Then where it has to be connected. It will leave the net like that. So this is an open violation. These all are reported in physical value. That is DRC and MBS. So at the time of sign off checks, we'll have timing sign off. Okay, and physical verification like DRC, LBS, and LEC. LEC is a standard solution to check the design functionality, whether it is working even after routing stage. And before GDS generation also, we generate a Verilog code for LEC verification. Once this is done, then we'll send the GDS file to fabrication. So these are the different synopsis tools used for VLSI. Whereas coming to cadence, we have IC 61 or purchasing. For synthesis, it is design compiler. Okay. From cadence, we have this. For placement and routing, we have Novus. And SPEF and extraction, we have star RC, we have Quantus QRC. For HTA, we have prime type. From cadence, we have 10 plus. For physical verification, we have ICV tool, we have Asura, PVS, Pegasus. Power sign off tool, we have prime power from Synopsys, Voltas, IR drop analysis from Cadence. So these are the wide variety of tools in the market available. These are the top Indian leading companies. And we use most famous physical verification tool in industry. This is from mental graphics, that is Caliber. This is the gold tool that we call gold tool, which gives very accuracy outputs for the foundry for fabrication. And nowadays, other tools are also getting qualified by the foundries. Okay, but the most famous tool for physical verification from mental graphics is Caliber. So we have a cross-platform design source. So what we do is we have a circuit design in Virtuoso. Okay, we have a mixed signal design. We have PNR design in ICC. So we have interoperability between Virtuoso and ICC. So we'll club these two designs from two different EDA tools, and we will do a physical verification with third tool, that is Caliber. So this interoperability between EDA companies is possible based on PCL script. So EDA CAD application engineer is very much talented. Okay, so to do this kind of practice, even EDA CAD application engineer is a job in VLSI industry. Okay, so this is the vast variety of openings in VLSI. Hope everyone is clear with this. You are able to follow Tarak, JD. Someone please reply, yes or no? Yes. So as a part of synthesis, what are the inputs we are giving to the tool? So targeted libraries, okay, .lib files, .hdc files, and RTL coding, and HDC constraints. And after synthesis, translation, optimization, and technology mapping, we are getting a gate level netlist. So the gate level netlist is also a .b form, very low form. And to set some timing constraints, we are using HDC. So create clock, create generated clock, or set max delay, set minimum delay, input delay, transition delay, output delay. So these are some timing constraints. Okay, these are some design rule terms. Max transition, min transition, max capacitance, minimum capacitance. Okay, so these are the some design constraints we are setting in the stage of synthesis, and we have follow some outputs after synthesis, that is Verilog netlist, that is .vr.vhd, and constraints file Verilog netlist constraints files.sdc, and reports which are related to area, timing, and power, and even quality of report, QR report. How good is your synthesis design for next level of floor plan or physical design? So this is a practical example of Verilog code after synthesis, mapping to the technology library, and converting RTL to gate level netlist. With optimization, we are getting this kind of hardware description language mapped to a standard sense library. Okay. So give me a 2 minutes of break. I'll fetch some water and come back. Okay. Sorry for the delay, more time. Why the participants count is fluctuating? They are joining, they are leaving. Okay. So next, after synthesis, we have to move to the floor plan. So in floor plan, what are the lists of files, folders, how we have to update? So that is will be taken care. Inputs list, like mainly these are the most file formats we use for physical design, like .tf file, technology file, and table lookup files, max and min table lookup files. This is library exchange format, left file, and liberate timing library, .lib, gate level netlist, .v file, standard design constraints or synopsis design constraints like .sdc. So what TechLeft contains? So TechLeft contains the name, number, conventions of layers and wires, physical electrical characteristics of layers, and spacings between the layers or metal routings, pitches, and electrical characteristics, and density in process. Next is table lookups. This will be a Excel sheet or a table which will have RC parameters. Next is layout exchange format. Layout exchange format contains physical information of standard cells, macros, packs. Contains names of the pins, ports, and pin layers, port layers, ground connections, signal net connections, and all those informations. Size and height and width of the symmetry of the coordinates of the layers. So we have a metal. So what is the symmetry of the metal? It has some width, thickness, and height also. So that is the symmetry. Next is library type. We having the information of transition, capacitance, delays, standard cell delays. They are related based on the RC values. Tau is equal to RC is the delay formula. So the same way, if we have a net, okay, that net has some resistance and capacitance. So based on that, the delay tables are designed using .lib files. Next is Verilog netlist or Verilog file. Next is design constraints. Design constraints are related to design and user constraints. So clock definitions, clock uncertainty, and timing exceptions. All these are reported in the SDC file. So what is block level design? So we have a full chip design and block level chip design. The full chip level is the SoC design. And if you are picking on Bluetooth or wireless chip, that is a block level. Floor plan. So what is floor plan? Designing or describing the core size, die size, IO offset, and aspect ratio and core utilization is floor plan. That we decide. Okay. At the time of floor plan only, we will decide how to place the macros and how to do the power routing estimation. This is the floor plan step. We'll decide the core area and die area and the IO offset. Core to IO clearance, macro to macro placements, IO pads, standard cell rows. So all these are defined at the stage of floor. And after this, the slides are going very fast. Okay, when I'm scrolling, doesn't bother. Core area depends upon aspect ratio, height and width of the cells. And core utilization depends upon the macro area, standard cell area, by total core area. So this is core utilization. The core utilization is 60% is like this, and the core utilization is 85% is like this. Next is ports placement. So we have pin connections. For that pin connections, we have to give some port names. So the port names are described in the Verilog file and left file and macros placement. So there are two types of macros, hard macros and soft macros. So when we do the placement of macros, okay, so we get in the two forms, soft macros and hard macros. Hard macros are logically fixed and soft macros are not fixed functionality, but we can have the permissions to change the logical behavior or functional behavior of the soft macros. So macro placement guidelines. So macro should be placed in corners of the core area. If you are placing in the middle, the routing net will take longer path. So this is not suitable. Next is placement of macros. So if the two macros sitting on the corner of the left top and the corner of the right bottom, so the nets connecting to each macros will create routing congestion for other standard cells. So we'll move the two macros to the nearby location with offset. The macro to macro, we have certain distance. So these macros are communicating each other. So we are making to sit together in one place in one corner. Either this macro should be brought here or this macro should be set here. So when we click on the macro, we'll get a fly lines, these fly lines. So which are communicating which what cells. So if the macros are communicating with the more side of the IO pins, then we are moving it to the IO side. So this is how we do the linear placement of macros. So if we have this kind of crisscross routing, okay. So what we will do, we'll try to flip the macros in right direction to set the routing to be linear. Next is halos. Halo is nothing but a blockage. So not to place communication between macro, so all the beside logics, we create a halo to avoid congestion. So macro to macro channel, and if there is no channel, there is no communication between these two macros, we can place it together, and these pins can communicate, this side pins can communicate. So if there are no pins this side and this side, we can put close to each other. So this is how we will take care. So if the known only, if the logic is known only, we can do that. Else we cannot do. So physical only cells placement. So physical only cells placement is for DF, design for manufacturability. That is handicap cells, boundary cells, vent cap cells, V-cap cells, tie low, tie high cells, spare cells, and filler cells. So some places in the chip will be empty. So in that places, we have to fill with metal to avoid design rule manufacturing. So for the foundry sake, we will fill this physical only cells, but that doesn't have any logic. Next is power plan. So power planning, we will do the ring power. First, we will do the ring placement, power planning, and next we will do the stripes placement. And based on the stripes, we will route the nets from power grid to the macros and standard cells. So how many straps, how many rings, how many power pins or power grid are required is based on the calculation of power. So this is block level and this is top level. Yeah, good, Tarun. You have done a very good job. So you have given a general document using Cadence. So using Cadence tool, we have done a lab session. So as I have told you, that is proprietary design confidential for my company. So I just showed you how you should use the tool for learning. So our Blackbucks team has generated a generic tool flow for you. So initially after synthesis, so using the tool, how to do the floor plan ready, placement ready. These are the following steps. So once you've done the design ready, you will be getting the floor plan window. So using this floor plan window, you will be getting the core area, the area. So here in the corner, we are seeing the standard cells. So when we perform the placement, all these standard cells get placed in these color lines. So this is how the placement happens. So if we have the nets, okay, which are communicating inward input, their direction to the inside. And if they have communication towards the output, they are communicating to the outside. And here we have done the placement of pins on the three sides, left, right, and bottom. And even if we do the top, the routing happens to the top side also. So next is global routing. So once after the global routing, we will get the more congestion in the routing. So we will use select to clear the DRC violations and generate the GDS file. So this GDS file is submitted to the contract. Next is, so this design of CMOS inverter. So this is covered as a part of analog simulation in Cadence Virtuoso. So what we have done is, we have done a Cadence circuit design of inverter. So for that inverter, we have written a analog mixed signal test image using ADE assembler. So for that, they are having a functionality. We have different sources, voltage sources. Okay. So using the pulse source, we are passing this pulse to this PMOS and NMOS. So based on this pulse, this capacitor will receive the output. So this is plotting the graph of inverter. So this is all about the tool options. Okay. So once you are into the industry as a fresher, you will be getting small amount of enough time to learn the tool. So if you are trained with the tool, directly you can go on roll for a project. So taking the inverter, okay. So we have done a analog test bench. So we are passing the pulse as the input. So here it is 0, but the inverter output is, if we are giving input 0, it is positive output. But so this is the timing diagram how we get using synopsis. This is completely synopsis flow using custom designer. So this is circuit diagram, CMOS inverter circuit. So whatever the parameters we have. So if we see the parameters, sorry, this is not moving. So this is the width. Okay. W is the width. So that is the charge flowing from source to drain is 0.21 micrometers. That much distance, if you are applying the gate voltage, how much time it should take to flow the charge. So all these parameters we can define in custom circuit. But whereas in physical design, we will have the predefined cells. That is library characterization. So we have the jobs in library characterization also. Okay, this is dynamic way of defining the parameters for a cell. That is transistor or MOSFET. But whereas in physical design, we will have primitive standard cells. Those are already defined parameters, which are huge amount of code for a cell or a characterization of a cell. So that's all from my side. If you have any questions, we'll take it further. Okay. So in detail, we have covered all these topics in the classwork and coursework. Okay. If you have any questions, we'll move further. So please, students, post your questions related to subject in VLSI. And this is just a gist of learning. Okay. So if you want to go really into the career path of VLSI, you need to learn very much detail. Dear students, do you have any questions? Please someone reply. Are you able to follow the concepts? Tarak, so are you exercising about cadence in your KL University? Are you sitting in your cadence lab? Tarak, I think the mic is enabled. Users can enable their mic and they can speak. Tarak, are you able to speak? And there is another person also, Bhuvaneshwari. She is also having tools in her college. Abhi, you are also from KL University? Yeah, please. This is a non-technical suggestion from my side. There are very bad viral fevers due to mosquitoes, okay, in the environment all around the world. Okay. So please be aware about malaria, typhoid, dengue, or chikungunya. The disease is caused by mosquitoes. Okay. So this is a non-technical discussion in our subject. So as Tarak is suffering from fever, so he is unable to speak it seems. Okay. Please be healthy conscious. Do not eat outside junk food. Most of the time, take fruits and homemade foods. Be very healthy to survive the next generation. We are in very much advanced technology. Okay, we are already surrounded by too much technology aspects in our surroundings. We have around almost 10 to 15 towers, which are completely radiations. Okay, it's like robot. I can say. We don't see any sparrows, parrots, or birds which are flying here in our environment in Hyderabad. Okay, so be aware about that. Okay, give our next generation and allow our next generation to live on this earth planet. So be updated with the technology, but be the limited usage of the technology. So any questions related to the technical part, learning of VLSI? Tarun, you are in the class? Who is the Blackbuck host?
Yes, sir.
Tarun or
Tarun, sir.
Tarun? So, how about their assignments, questions, everything is solved? So, do you students have any assignment question? You please try to reach Blackbucks people. They will help you. Okay. So, if you have any questions, please post. Else, we will end the session for today and we'll proceed if you have any doubts. I'll wait for 5 more minutes. Which is the one must do project you suggest us to do, sir. Janavi, your question is not clear for me. Which is the one must do project you suggested us to do, sir? One must project. What is that project? Tarun, can you help me? I don't remember currently. Abhi, what is your interest in the subject? What all subjects you are familiar? Abhi? Yeah, don't worry. You can post it. This is an open chat. Okay, I am not a perfect in this imperfect world. Physical design. Abhi, great. So you need to have a skill of EDC, okay, electronic design circuits and electronic circuit analysis, network theorems, and transistor designs, transistor modeling, and all those design to clear just the interview part. And some scripting languages like TCL, C shell. Okay, so you can get into the job in physical design. There are too many openings. Okay, too many. Like every day I see 80 to 100 openings in physical design in my LinkedIn. Okay, they are just coming like notifications to me. We can do any course, sir. So, Abhi, I would prefer. Okay, so anyhow, learning the course will take 1 year. Okay, so better approach for MTech in some tier 1 colleges or premium colleges where you have tools. Okay, and do 1 year MTech and 1 year tool work to get the project done. What is your opinion, Abhi? This is my opinion or suggestion. Okay, so anyhow, learning the course. Okay, you will get 1 year. It will take 1 year. If you are doing MTech, it will take 2 years, but you will get a post graduation. This is a plus point. So if you are learning in tier 1 colleges, you will have EDA applications like Cadence, Synopsys, Mentor Graphics, all these things. And you will have a very good amount of placements also, direct. So I can say as an IIT Hyderabad senior research fellow, okay, so each and every MTech student, the package we cannot see in our bound. As a fresher, MTech fresher, they will nearly crack 3 to 4 interviews MNCs, TSMC, NXP, TI, Qualcomm, Intel, okay, Silicon Labs. And the package is approximately not less than 30 lakhs and a maximum of 70 lakhs. As a fresher, MTech fresher, okay, if you have a loan of 7 lakhs or even 17 lakhs, okay, for education, with that 70 lakhs, we can clear it in 1 year. Hope if you can dare this way. Is it a valid important point, right? Yes. The same way I have done my BTech, MTech, and physical design, and embedded Linux engineer, and CAD engineer. So this is my roles about my career. Next, any more questions? So there was a question from Janavi. So Janavi, can you please elaborate it? Which is the one must do project you suggest us to do, sir? So you want me to suggest which project you want to do it for your academics? Is that question, Janavi? No, sir. Then has a coursework. What is the yeah. So one good project to start as a beginner. So beginner, you can start with anything. So at the time of my BTech, I started with physical design. Okay. When I was in my final year, I started my project with physical design. So at that time, we don't have any tools. Okay. So we have a circuit analysis. Okay. So some open source tools related to microwave. So I remember my VLSI teacher helped me a lot for designing op-amp comparator. So using this, I have designed op-amp comparator and I have got the first person to delivery the VLSI project in my academics in that current year. Okay. Okay. So after that, I got encouragement from my management to give a guest talk on VLSI at my BTech level in 2012. So after that, we have licensing tools like Synopsys and Cadence. So I was not familiar with the Cadence. After coming to my MTech only, I am familiar with the Cadence. But before that, I am familiar with Synopsys tools. So Synopsys custom compiler, custom designer. As I have told you, in my MTech, we have 6 subjects per semester. For 6 subjects, we have 6 theory, 6 practical, 6 technical writings, and 6 projects. Suppose we have a subject called VLSI, digital design through Verilog. So what kind of project we have to choose? We have to choose Verilog front end or VHDL front end. We have to take an IIDT research paper. And this is another challenging for us. We have to take a real-time IIDT research paper. And solving that paper, we have to discover the logic. There is no direct schematic. As I have shown you carry select adder, there is no direct schematic on the paper that is published in IEEE. So we have to extract the schematic, logical schematic or architecture of the digital logic, and we have to code it. And our professors or the mentors who guide us, who give us mark, they used to see our approach, not the output. Okay. So this is very much important. In every educational tier 1 colleges, they see our approach. Firstly, if our approach is correct, they'll push us. If the approach is wrong, you take time and make your approach very proper. So after collecting that IEEE papers on our interest, I have selected network on chip. 16x16 network on chip. So using this network on chip, I have developed a 16x16 matrix network on chip. Writing a Verilog code using a verification methodology like UVM, PMM, or OVM. So I was familiar with UVM just for academics purpose to clear my subjects. I'm not a good verification engineer. Okay. So using this UVM methodology, I have written a Verilog system Verilog code. Okay. By taking help of my friends, mentors, and seniors, I have written a UVM methodology and I have tested the RTL verification. Once the RTL verification is passed, so now it's my turn to play with synthesis, physical design, place and route, and all those things. So I am the first physical design engineer from my university. So I got it done the project completely. So rest of the people who took my documentation and they did on their own as a manual reference. Okay. So I helped my friends a lot that I am very much interested. Okay. So they have learned based on my document and they have done. So like this, the project you can choose in any domain, but try to take a real-time example. So as our we are aware about IEEE papers, so take some real-time paper, either it is circuit design or a Verilog design or a physical design or anything. So take that design and try to extract the schematic or the logical architecture and try to develop the circuit project. Sir, should we complete employability tests? Krishna, Himaja. So these will be answered by Blackbucks in the last 5-10 minutes. Okay. Sir, what is the last date for completion of employability tests? So this also is the Blackbucks. So apart from this, we used to do technical writing. Technical writing is nothing but, so whatever we have learned in the coursework, I have told you as a digital design through Verilog. Okay, so I have to write a technical paper. So the technical paper should be unique and no plagiarism. I have to publish this white paper in Scopus, Springer, or even IEEE. So we are not directly to publish these papers into IEEE. We were trying in Scopus and Springer. So we tried and we published a white paper on digital design through Verilog for network on chip in Springer. And next, after that, project. Next is technical writing. And we have a lab exam also. So they will give us some random. So as in our lab tests, they used to put some slips, okay, in our BTech. The same way in our MTech also. Luckily, on the tool login, we'll have a question. So we have to design that question in the given amount of span of time, like 120 minutes or 100 minutes. The timer will be running. So if you fail to submit the lab test, we are failed. And there is no more chance. And we are lost the credits. And remaining 3 things, we have to pass the subject. Lab, project, theory, and technical writing. Everything has a equal weightage. So if we fail any 2, we are failed for that semester and the project. Okay, we have to retake the exam. If you are passing any 3, we are safe side. So this is the challenging type we faced. Sir, only learning digital electronics can get a job in VLSI? Yes. Maybe yes. So I am the person who has knowledge in digital electronics, and after entering into the industry, I got a chance or opportunity to work in mixed signal design flow. So the mixed signal design flow is like PLL design. So in the PLL design, we have to design 2, 3, 4, sorry, 4 digital blocks. So for that 4 digital blocks, we have received a Verilog netlist for synthesis physical design. So that is analog amount of design methodology. So as a digital electronics engineer, you should have analog electronics subject knowledge to clear the entrance initial JD. Okay, take it granted. Okay, so when I was approaching the interviews, okay, so initially I failed to clear my interviews in VLSI. So later, after appearing 1-2 interviews, I got to know what is the method and how, what are the criteria interviewer uses as a fresher to cut off. They give questions from arithmetic, reasoning, aptitude, VLSI, digital electronics. So this is non-technical subjects. And coming to the technical subjects, just small piece of Verilog code like half adder and using operators, using shift operators, using concatenation operators, and very small logics, but they are different questions. The same way they give CMOS inverter circuit. And they give some circuit and they ask us to calculate gain. Okay, and the voltage output and what is the load of the circuit. In this way, they used to ask the questions in the interview. At least we will have 4 to 5 questions from digital, 4 to 5 questions from Verilog, and at least 5 or less questions from transistors or digital domain. And next is aptitude, reasoning, and all these things. As a fresher. So my first project is related to Bus, Advanced High Performance Bus, AHP, protocols and interface. So this is my MTech first semester subject, and I have told you, okay, 470. My first VLSI project is circuit design. Okay, so using microwave, I have designed a op-amp comparator. in my BTech project. So we have mini project and major project. So mini project we have opted for embedded systems, okay, and major project I have opted for VLSI. So as the project leader takes the decision, the team members also has to follow. So I was the project leader in my BTech. So I have two team members. So they used to help me a lot. Rather than digital electronics, okay, learn EDC, electronic circuit analysis, uh, network theorems. Yes, this is very important. And yes, yes, very good for getting VLSI job. So initially you have to clear the written test for a fresher. If you are experienced, based on your experience, the interviewer will take the questions. If you are a fresher, you have to take the written test for all the subjects of your engineering related to electronics. Hope everything is clear, JD? Oh, okay, sir. JD, see, I have told you, initially I failed two attempts of my VLSI interview jobs. Okay, so not to, I just not wanted to reveal it, but so initially I got a job offer in Signed Infotech company in Hyderabad. Okay, so as a placement from our university and college, but it was not for the VLSI, it was for software. So I strictly said no to get the job in software. As I have learned BTech in electronics and communication engineering and MTech in VLSI and embedded systems. Okay. So I just directly wanted to stick to my role in career for 4 months. So I have stick to it and I am working currently in CAD application. So I have passed uh, physical design, synthesis, uh, timing design engineer, and at last CAD application. So it's not my great, okay, it's all my learning and career path. And seeing all my see, even I have a books of Razavi, even I have a digital design through the Love book every day with me in my room. Okay. See, seeing this book, my son is also starting learning about microprocessor. He learns two spellings about operators, arithmetic operators. He is just a grade one kid. So that is how one should have a passion about learning the subjects. Okay. So I encourage all the students, advanced congratulations for all the VLS engineers to be seen shortly in Hyderabad, Silicon Valley. Okay. So the Silicon Valley from Bangalore has moved to Hyderabad. So, so Bangalore is saturated for silicon now. So Hyderabad is growing. And next, the city to grow in India is, someone can guess? Does someone has knowledge about silicon cities in India? The first silicon city in India is Bangalore. Second is Hyderabad. Third is Noida. Noida has companies, but there is no more of the VLSI companies. But we have VLSI companies in Noida also. And the fourth one is, someone can guess? It's in Karnataka. Hubli. Hubli. Okay. So thank you all. So this will be our last session. If you have any on-demand session, Blackbucks team will intimate me to connect with you. So I congratulate everyone for having a great, bright future in your career paths. Grow as much as you can. Okay. Thank you. Blackbucks, it's your time to take the call. Okay. Please clear their doubts. Thank you. Good night, all. Happy weekend too.
Hello, students. Now I am going to give you a small announcement about the project works and how to do it. Could you please reply yes in the chat box if you can hear my voice? Okay, students. Everybody is assigned a single project to each and everyone. You should do it individually. And each project is conducted in the form of hackathons. And our hackathon consists of 4 parts. First part is abstract, where you should give the info. I'll share the screen. I'll show you. You can see here, right? This is a simple IEEE paper on 9-bit UART model. You can see here, right? Everybody should write abstract about the project we are doing. You can see here, right? We just write about the concept and the details what we use in the project. Everything in the abstract model, and you should submit it in 2 days after project is given to you. After completion of the abstract, you should submit the block diagram. Block diagram is, you can see, right, similar to this. You should draw the block diagrams or simply use some paints or files, anything. These block diagrams or state machines. You should submit these block diagrams. And another third is code, source code and test bench code. You should submit the code and test bench codes similar like this. Verilog code and test bench code. And fourth, you should document this whole project properly, like write the project name, abstract, description, block diagram, code, test bench code, and simulation results. If possible, paste the schematic diagrams, RTL schematic diagrams or synthesis diagrams if you have tools. Or else there's no problem about that. You can simply paste the simulation results. Hello students, did all of you understand the how to file the document and share to us? Okay, I'll share you the attendance link. In 2 minutes, I will end this session. This is the last session for us. 2, 3, B9 block diagram means you should simply draw the block diagram. So Naga Chaitanya, okay, where we have to upload the document. Naga Chaitanya, in the current website, what we will give the links. We will give you the links, and where should we upload the documents? Submission day. Triveni final submission day We will inform you that, sir, Triveni. Steps. What is the last date for completing employability skills? Okay, I will contact the team and I'll give you the information about employability skills. Currently, I don't know anything about that. Satvika, I'll contact the team and I'll give you the information about that. Grant test. Don't worry about grant tests and employability tests. Just concentrate on projects. We will assign your projects shortly and you can work on that. I'll repeat once again the steps. Your project should be done in a hackathon format. There are 4 rounds in our hackathon. First round is we should submit the abstract. Second round, we should submit the block diagrams and the concepts related to that. On what base we are writing the Verilog code. Third step, we should write the source code and the test bench code. And in the fourth round, you should submit the whole project in a document format. First, at the starting, you should write the project title, abstract, the concepts related to that, block diagram, if any FSMs are used, finite state, machine states. And at the last, you should write the codes and test bench code. And you should paste the simulation results. If possible, you can also paste the synthesis results. If not, it's not a big deal. P. Akshaya Satvika, did you understand the format? Okay, students. I'll post the attendance link. Fill the attendance link and correct 1 minute or 2 minutes. I will end the session. This is the last session in our internship program. We'll contact you for the projects and all. We will explain how to do the projects, and if any doubts, you can contact us. Pravina, last date in project. Pravina, up to now, we didn't thought about that. A last date. We will give you the last date. As you can contact me by email or any contact support from the website. Okay, guys. Good night. I'm ending the session. Krishna, you should complete the employability test, Krishna. It's mandatory. Okay, guys, see you.